Okay, so now let's talk about replication and sharding when it comes to databases. And these are actually two pretty different things, but they're also related, which is why I want to cover them together. So let's start with replication. Let's say we have our database and we just have a single database node, whether it's SQL or NoSQL, it doesn't really matter too much. All of our application data is on this database. Every read, write has to go through this single database. And maybe that's perfectly fine while we have a small amount of traffic, but as we get more and more traffic, maybe we have too many connections on our database at the same time, or maybe we're just processing so much data from our database. Every query has to read through so much data and do so much stuff that we can't handle as many requests as we're getting. Well, that's where replication comes in. We take our database and actually replicate it, create a copy of it, and then we are able to handle more requests. But it's not this simple. Replication has a lot of nuance with it. There's a lot of trade-offs that you actually have to make. There's a lot of decisions that we can make. Let's take a look at an example of leader-follower replication. This is also known as master-slave replication, where the leader is the master and the follower is the slave. In a lot of textbooks and other material, you may see it referred to as master-slave. But that's starting to become more of an outdated term, and you may see it referred to as leader-follower. So that's what I'm going to be sticking with. So the idea is pretty simple. We have a database and we replicate it and create a follower database. So the leader is the one that's responsible for, replicating its own data to one or more followers. Now the followers could actually also replicate data as well if they wanted to some other followers, or maybe the leader will be the one responsible for replicating to all the followers, but that doesn't really make a lot of sense. It's okay if, the followers pick up some of the work if they're able to do that. The more important thing is, what is the leader going to be doing from the client's perspective? And the client could be, an actual user, but in reality, users don't directly talk to the database. They actually go through our own application. They'll be making a request to our application, and then our application will talk directly to the database. But in general, from some client perspective, we can read from the leader, and we're also able to write data to the leader node. Now with leader-follower replication, we actually are only allowed to read from the follower database. We're not allowed to write to it because the way our replication is working, our leader is going to replicate its data to the follower, whether we have one or more of them. But if we allow clients to write data to the follower, then the follower in this case is not replicating its data to other nodes. So if we were allowing people to write to the follower, obviously things would not work. We would have some data here that doesn't end up getting replicated to the leader. And then if somebody tries to read from the leader, they will not see the up-to-date data from the follower. So this is one way of doing things. Now, obviously, with this, we are able to scale reads, which is usually more important. Think about most applications you use. Are you writing data, or are you just loading pages and reading other people's data? Usually reading is more common. So this is a relatively simple way to scale up our reads. And the way we actually do it with replication, there are many different strategies for replicating data. The main trade-offs, though, is when it comes to asynchronous versus synchronous data replication. As the name implies, asynchronous is when we don't have to do it immediately. Like a client writes some data through the application, and then they write, some piece of data over here onto the leader. So if the leader is doing this asynchronously, the leader is going to at some point take this data and replicate it to the follower, and all the other followers will also get the data at some point. That's asynchronous. We don't know exactly how long it could take. It could be on some schedule, like every hour the leader will do that. Usually it will be more frequent. But it could be based on some schedule, or it could just be, a few seconds later, the leader will take that transaction that the client wrote to the leader and then, make that same transaction on the follower. And this works. The follower will have up-to-date data, but the downside is with asynchronous replication, other clients who are reading from the follower may see inconsistent data. We will have inconsistencies between the leader and the followers, at least for a short amount of time. So if we're okay with that, this works. Maybe for a few seconds, some clients who are reading from the replicas will see stale data. That's a trade-off that we make. Now, with synchronous replication, every time a user has a write transaction on the leader will actually stop and immediately take that write transaction and immediately replicate it to the followers. Now, at first, this seems really good because we won't have inconsistent data. As soon as that data is written to the leader, it will also be written to the follower. Like, there's no inconsistencies with the data between leader and followers. Anytime a client reads, they will not see any stale data. But this actually does have a negative. There is a downside to doing synchronous replication. And as you can guess, it is with latency. If we are replicating data immediately, it does still take time. It does take time. As soon as the user writes data to the leader, then the leader will write data to the follower, and only after that's done is the transaction considered complete. From the client's perspective, we will not tell them the transaction is complete until we replicate the data as well. And if the replicas are in different parts of the world, you can imagine that this will definitely increase the latency significantly. And I think these are really the important points to consider when we are talking about replication. Now, with this type of replication, not only is the benefit that we're able to handle larger read scale here, we're able to handle more reads at a time, but we've also sort of increased our reliability and availability, because if one of these databases goes down, like for example, if the leader goes down, at least we have a mostly up-to-date replica that has most of the data. So if the leader goes down, at least we have a replica that could take the leader's place. So that's another benefit of replication in this case. Now, there's also leader-leader replication where we have multiple leaders. This is also called master-master replication or multi-master replication. Of course, the benefit here is that we can actually read and write from every single node. So not only do we scale up the reads, but we also scale up the writes. This is really, really powerful, but as you can imagine, it comes with its own trade-offs. Instead of just having a single leader where we then replicate to the other followers and then maybe the followers can replicate to the other followers, here we have multiple leaders. We only have 2 in this example, but we could have even more. And I'm sure you can imagine replicating data between multiple leaders can get very, very complicated. Of course, these replicas are going to go out of sync, right? Like some data is going to be written here, some data is going to be written here, and then these have to kind of swap that data. And these are definitely going to get out of sync, and these are not going to be very consistent. Like that's going to be the downside here. With multiple leaders, we're definitely going to have lower consistency between the leaders, between the nodes, even though we are able to scale up the writes. So if we do asynchronous replication here, our data is going to be loosely consistent, but it's definitely not going to be consistent. And if we do this synchronously, then we're definitely going to see much higher latency depending on how many leaders we have and how they're geographically distributed around the world. Probably the main reason you'd want to use multi-leader replication is if you had, let's say this is our world map. We have one half of the world over there and one half of the world over here. If we had, a leader serving every continent of the world, let's say we have a database over here and we have a database over here. Everybody from this half of the world has their own leader, and everybody from this half of the world has another leader for them. And that's pretty much it. So if these 2 database nodes become out of sync, it's okay, because everybody from this side of the world is going to mainly be interacting with one of them. Everybody from this side of the world is mainly going to be interacting with the other one. Now, sometimes people from this side of the world might fly to the other side. That's okay, because we are going to keep these in sync, but maybe every hour or so we sync these together and then give them all the up-to-date data. But we don't have to do it immediately. So this is a really good use case. This is kind of the main use case of multi-master, multi-leader replication, being able to serve different parts of the world roughly independently. Okay, now let's talk about sharding. And the thing about sharding is that talking about it is actually not super complicated. We can talk about it in a pretty simple way, but implementing it is very, very hard in practice. And you probably won't be going into the details of sharding in an interview setting. It can get really, really complicated. So we'll mainly be focusing on the basic ideas and the basic trade-offs that you'll be talking about in real interviews. Now, what is sharding and what problem does it solve? Well, Similar to replication, if we have a database and it's getting so much traffic, so many reads or maybe so many writes that a single computer can't handle all of it. I mean, we can vertically scale our machine, but we can only go so far with vertically scaling. So then we try to horizontally scale this database. One approach would be with replication. We can handle a larger amount of reads with replication. We can even have a strategy for writing and being able to write more data with replicated nodes. But sometimes that's still not enough. What if we have such a massive amount of data, not terabytes, but petabytes of data, massive amounts of data, and certain queries, right? Like searching that amount of data in a single machine is way too difficult. Queries are taking multiple seconds, right? Imagine you load Twitter and it takes you 5 or 10 seconds to see your Twitter feed. That's such a massive amount of data that a single query is going to take seconds and seconds to retrieve the data that we want. So this is where sharding comes in. We actually not only put this data on multiple machines, on multiple nodes and computers, but we actually take the data itself and then split it into smaller databases. I mean, literally, we take a table, right? Like we know every table has some schema, every table has a bunch of rows, and we take half of those rows and put them in one of the databases, and then that database will be on its own machine. That's very important because if we put both of these on the same machine, that's not really solving any problems. So we put them on different machines so we have more resources. And then, the second half of data in a table goes to the other database. And of course, we could have more than two, smaller databases, but these are called shards. We've taken our individual database and broken it into smaller pieces, aka we sharded the database. These are database shards. And then if users want to read and write data, they will go to the individual components, the individual shards. And not only are we able to handle more traffic, because now maybe half the traffic will go to this node, half the traffic will go to this node, we'll be able to handle that, but the queries themselves will go faster because this one has half the data. So presumably a query on this shard will be a little bit faster than on the original database. Same with this component, and we could have further broken these down into smaller shards. Now, how do we decide how to actually distribute the data? Like here, you can see half the data goes here and then the other half goes here. How do we decide what half of the data goes where? Well, there's a couple approaches. The simple one is range based. So we would take some range of values here and some range of values here and decide. Now, what value do we actually use? Well, that's called the shard key. So this is actually a special value that's used to decide how to split the data up. And one type of shard key is a range-based shard key. So for an individual table, we would typically choose the primary key for using how to actually split the data up. So assume that, this table has some primary key, and using that primary key, we say that some range of values, like the most simple one I can think of right now is male versus female. If we're doing this based on sex, for example, like males go to this shard and females go to that shard. And this is a really basic one because this is actually discrete. It's like 2 values. Another one we could do is based on last name, like the first character of your last name. So from everybody from A through L or something like that is going to go to the first shard. If your last name starts with any of these characters, you're going to go here. And then for the second half, maybe it's M through Z. So if your last name starts with a character in this range, you will go to the other shard. So this way, data is consistent, sort of at least. Like we're just looking at it from one table's perspective, but everybody, from this table will go to another shard, and then everybody from this portion of the table will go to another shard. But as you can imagine, running joins on, 2 halves of a table is going to be pretty complicated. In fact, it's going to either be really slow or it might just not work. And this is, and now we are starting to see the complexity of sharding. With just a single table, maybe it's fine. But if we shard a second table and maybe data from that table is related to the first table, so how do we keep things consistent? How do we make sure that, the corresponding data from the first table is also matched to the same shard? This is where things can get complicated. You have to implement a lot of custom logic depending on how you do things. Instead of range-based sharding, we can also use hash-based sharding, and this is actually a use case for consistent hashing. Consistent hashing is another algorithm that's used to shard data, to decide how to distribute data into multiple shards. So while things can get really, really complicated, these are the basics that you'll really need to know for system design interviews. And it's also worth mentioning that with sharding, SQL databases, popular open source SQL databases like MySQL and Postgres, they do not have sharding by default. If you want to shard your relational SQL database like MySQL or Postgres, you will have to implement the logic for that yourself at the application level. You, from your own application, will have to decide how to, shard the data, how to know where to find data, which shard has the data that you're looking for, and all that. And it makes sense because SQL databases naturally are not meant to be distributed in this way. When we do this, we're losing the consistency that we get from ACID, where we know that foreign key constraints and all the other constraints that we specify in our database schema and all that is going to be enforced. We lose that with distributed data and with shards. But typically most NoSQL databases will actually have sharding by default, like it will be implemented as a part of the database management system. And that's because NoSQL databases are naturally meant to be sharded. That was the whole point of NoSQL databases, that we can horizontally scale them better. I mean, yes, our data will have to be split up into shards. That's okay, because we're not going to be joining the data very much. We're not going to be having foreign key constraints. Our data is non-relational. The data doesn't even have to be consistent from the nodes. It will be eventually consistent. I hope this is starting to make the difference between SQL and NoSQL a little bit more clear.